Hello, I'm Stephanie Soldavini from Politecnico di Milano in Milan, Italy, and our paper is called Compiler Infrastructure for Specializing Domain-Specific Memory Templates. This project is in collaboration with Christian Pilato from Politecnico di Milano and is a part of Everest, an EU-funded project about the FPGA acceleration of big data applications. Such big data applications are typically computationally intensive, and we are focused on the creation of specialized accelerators, which are usually difficult to design and integrate. High-level synthesis can help with this, but currently, HLS tools focus on optimizing computation, and the memory architecture is built around that, merely sustaining the accesses as needed by the computation. However, in data-intensive applications, memory accesses are the bottleneck, and highly optimized computations are forced to wait on the memory. To remedy this, optimization should instead focus more on coordinating memory transfers. Carefully crafting specialized memory architectures for each accelerator can produce good performance, but the process is time-consuming and must be done for each new design. Domain-specific architectures, on the other hand, are more general and promote reuse by applying to many accelerators within a domain, but this comes with a sacrifice in performance. We propose an approach in between, using a domain-specific template, which allows specialization of various components. This template will be specialized automatically using a compilation flow based on LLVM MLIR. The input to the flow would be MLIR from domain-specific language descriptions after compiler-level optimizations. The first stage, data organization, would determine at the highest abstraction level the coarse memory structure, i.e., which data resides on or off chip based on user or compiler annotations, including the total amount of data, the sizes of the arrays, or the available resources. The next step, the layout phase, reorganizes the computation to better exploit local memories, either caches or private local memories. Then, in the communication phase, the prefetcher is configured to hide transfer latency based on the data access patterns. After this, the local partitioning phase determines the multi-bank PLM architecture, also sharing physical memories for data with disjoint lifetimes. Finally, the high-level synthesis phase uses existing HLS tools to generate the computation part of the accelerator, producing the complete synthesizable hardware description of the accelerator. The figure shown here is an example of an architecture where the memory system hides all of its implementation details from the computational part generated by high-level synthesis, only exposing the necessary ports for either fixed latency or latency-insensitive accesses. We aim at developing a completely open-source solution by using existing tools such as Nimuzine for memory generation and optimization, and Bamboo for HLS. But we also aim to be compatible with commercial solutions, like being able to use instead Xilinx Vitis for HLS. Some key observations. Platform-based design and orthogonalization of computation and communication allow us to perform a progressive refinement of the template. Our multi-step approach takes advantage of 3 levels of optimization. Code-level compiler optimizations rearrange the data accesses to increase available parallelism. Memory-level compiler optimizations rearrange the memory components and their interconnections accordingly. And finally, the high-level synthesis level optimizations rearrange the computational logic to exploit this parallelism. Lastly, we will also investigate using a circuit-based description of the memory template and its specialization flow. A circuit-based solution could also be used to replace the Nimuzine memory system generator, especially once we better understand how to integrate third-party IPs like memory controllers, existing memory blocks, etc. Thank you for listening. Please do not hesitate to contact us with any questions or comments you may have. More information can also be found on the Everest Project website.